So I put your tests in. Yep. They're kind of in there. I put them in yesterday. So if you saw your grade at all this morning, that was the same grade. I put it in 3 categories. It's kind of weird, but it's good enough for me. You okay with that? So that you kind of know which one you did good on and didn't. So it's, you got your multiple choice, you got your elements, and you got your free response. If you did not do well on the elements, you can always come in the rest of the try and pass the 50 elements off. Easy enough. So most of you did fine. And if you look at your grades and you're like, wait, I got 50 out of 50 on my elements and I spelled sodium like something, like I gave you plus, or I gave you 2 wiggle room. So if you missed 2, you still got 50 out of 50. Yes, sir.
Did anybody spell
beryllium? I don't know. My TA corrected him. So
You know how to spell really good?
probably not. And I don't care. So and then on the multiple choice, it was kind of weird. The way it exported, I wasn't able to change what it was out of. That was the plan. So I just added 2 to your score. So if you got more than 10, then that was why. I don't know if I did that yet. Do you have your grade? I can't remember if I added the 2 points yet. I may have. Okay. Anyway, I have the papers right there. I'll hand them at the end. Overall, you did really pretty good. A lot of you need to know that luster, which means it's shiny, that is a physical property, because we can see something is shiny without changing it. What else was missed a ton? The describing the test tube, most of you had a okay answer. I was looking for the word heterogeneous or homogeneous to be used. And I was looking for the word mixture and an explanation. A lot of you did not explain. That one you did explain, but this one, where it said a substance is found, yada, 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 justify your answer, you didn't do that. And then number 4, everyone drew it fine, but a lot of you didn't bother to describe. You just drew a picture. So anyway, overall, I thought you did fantastic. I don't know, we had a couple low scores and then almost everybody else did fantastic. Okay, so today we're going to cover a lot of stuff. Sound good? I'm going to unplug this fan because it's kind of loud and it's probably about time where it's hotter outside than in here. All right, chapter 2, once again, it's a lot of fundamentals. There are more things today that we'll talk about that are tested than there was yesterday. So I'm just going to jump on in. So today was a success when you can, whatever. I know these aren't great sentences, but know what to do if you are absent from class. I love all of you, but I get so many emails every day like, I'm absent, what do I do? All right, so let's okay. I'm not crying because I don't love you. I'm crying because I feel like it. All right. I have added yet another thing that maybe will make it finally crystal clear what I hope you do. I just realized I didn't do it in AP chemistry yet, but I will. So there is this, how to use this Canvas course. This has been in normal chemistry all year. I've now made a video that says the things that were written in typed words instead. I think the reading part was what was getting kids. They open it up and they're like, nope, ain't gonna do that. This video, it won't
Have a
be
lot
very
of
loud because
questions
I'm
coming
talking,
in.
but it will
Kids
tell
are-
you to first log into Canvas, and then that you can go check the
Might be
calendar.
Very crowded.
Raise your hands if you know how to check the calendar on Canvas. Okay, on a computer, it's on the left. On a phone, it's at the bottom. And if you have that's an Apple. I don't know what Android does, but I assume it's similar. It's just right there at the bottom. It looks like that thing right there. You can click, this is a video, so it won't work, but we'll just get out of there. Whoops, because we don't need to. We'll go to the actual real calendar. Maybe. All right, your Canvas calendars might be really full of stuff because it's all your classes, right? Do you have this menu right here to select which one you're currently looking at? I got a yes from at least one person. So we can turn the other ones off, and then that is just your AP chemistry calendar. So if you were gone today, you would click that and it would tell you what to do. Now, it doesn't always just say, this is exactly what we do. It sometimes just says, here's the class video for today. So this is yesterday. And you could watch all that. And while you're watching that, you'll realize every single thing we did yesterday, because I record every single thing we do every day. Okay, so that is an option. You could also, there's more options, and it doesn't, I don't know, that's probably the easiest. Come on, Tom. So we are now in chapter 2. So we have the reading assignment. Like, hey, I'm gone. Maybe I should read a few sections. I could figure out what section by looking at the calendar. All right. Or I could think, well, yesterday we talked about section 2.1. Maybe we're on the next section. All right. And then there's additional resources, and there's also the class 2 videos here. They're the same ones on the calendar. So there's 2 ways to do that. So that's how you go. And I'm not mad at people emailing me, but I feel as though I've explained it a few times. So raise your hands if you think if you were gone, you could figure out how to find out what we did on that day. Okay. I got like 1 this morning. I got 3 yesterday. I probably had 3 or 4 on Monday. So it's all right. It just takes time to individually reply. Okay, so hopefully today was a success because you know what to do if you're absent from class. All right, the rest we're going to describe the parts of the atom, which hopefully you can do right now. Explain and identify isotopes. These may not be in order now that I look at them. Answer simple mass spectroscopy problems. This is definitely on the AP test. They love this for some reason. They added it maybe 2 or 3 years ago, and they really love those questions, even though they're not even that hard. But that's fine. And then calculate average masses of an atom. This is not hard, but you need to know how to do it because it is typically something you'll see on exams. Okay, so let's fire away. All right. Up until now, we had Dalton that said it was a dot, J.J. Thompson that said it's a dot, but it has electrons. It has a negative charge and a positive charge because he knew it was neutral. Then you had Becquerel and the Curies that said, hey, something flies out of this atom. And then, okay, so then we had Rutherford, and he said, what? Tell your partner what Rutherford studied before this slide. All right. So Rutherford, he was examining the types of particles that came out that the Curies discovered and came up with the alpha, beta, and gamma particles and their properties. Now, he's going to step it up. And he's going to be like any little kid that finds a stick in the woods. And he's like, I'm going to pretend to shoot people with it. I don't know where that comes from, by the way. Like, oh, a stick. Boom, 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 boom. Okay, quit watching violent movies. But he thinks, all right, I now have these tools. let's blow some stuff up. So he decides to study the atom by shooting it with radiation, and specifically with alpha particles. So this is a famous thing, and it's called the gold foil experiment. And it's one of the fundamental experiments of all chemistry. Rutherford took a piece of gold foil, super thin, like super thin piece of gold, but he knew it was dense. So there was a lot of atoms, but really thin. And then he had his little lead block and a source of alpha particles, and he shot this piece of gold with these alpha particles. And his expectations, oh, well, I should say, he had this little ring around it that would phosphoresce, or it would give light off when an alpha particle hit it. So he was expecting all of the stuff to be just straight through, because they thought the atom right now was the gold, or the plum pudding, sorry. And it was just some positive goo with negative electrons hanging out in it. That's what they thought it was. So he just thought, all right, the alpha particle is going to zoom right through and hit this thing all right here. And he was sort of right. Most of them went right here, but some of them curved away, and some of them bounced very sharply back at the source. Alpha has a positive charge. So say it. This is great. Say it. Okay, you didn't go exactly where I thought you would, but that's fine. He was concerned that they would pick up electrons as they went through, but based on the charge of the gold staying neutral, he could prove that that wasn't happening. It was not stripping off electrons. Okay, now what I thought where you were going, this beam with some of them coming through and bending away, he was able to come up with the charge of the nucleus. Will you tell your partner what you think the charge of the nucleus is? You probably know, but tell them why from this. How do we know from this experiment? Any ideas? If you said, okay, I can't hear you through your mask. All right. So here is what he discovered. He discovered the atom had electrons in it, and that there must be something in the center, and it must be charged what? Positive. It had to be positive because it was repelling the positive alpha particles. They were flying in and deflecting away. Okay. Now, some of them bounced back, and so he hypothesized that whatever is in the middle must be really, really dense. So he is credited with the discovery of the nucleus by the gold foil experiment. I think that's a multiple choice. It's like two blanks. So-and-so is credited with the discovery of the nucleus by using the blank experiment, and it's Rutherford and gold foil. All right, so the alpha particle came in and hit whatever was in the center and deflected out like a pool ball. So it both bent away because it was repelled, but it also bounced off when it hit the middle. So Rutherford is typically credited with coming up with what we call, I call the Jimmy Neutron model of the atom. Do you know like what I'm talking about? Like tell me that's not Jimmy Neutron, right? He didn't know much more than that. He assumed there was a positive center and there were things flying around it called electrons. His model had a really big problem though. Someone said, okay, I believe that, but moving energy is supposed to radiate and lose energy. So why don't they spiral into the middle? And he answered that very technically. And he said, because he had no answer to that. So it was a model that made a lot of sense, but a lot of people didn't buy because he couldn't explain why the electron didn't just move into the nucleus and all matter would be a lot different. Okay, this is just going to summarize everything I just said. Since some of the particles were deflected at large angles, Thomson model could not be correct. Rutherford postulated a very small, dense nucleus with the electrons around the outside of the atom. Most of the volume of the atom is empty space. So he also was the first person to really say that the atom is mostly nothing. And it super is mostly nothing. When I was in high school, and this isn't perfectly accurate, but my chemistry teacher, he took us out to the football field and he put a dime at the very center of the field. And then he made us line up in the end zone. And he said, if this is the size of the nucleus, you guys are about where the electron is located. And it turns out it's actually a lot farther than that. So it's like maybe from here to the center. And between that and that electron is nothing. Absolute empty space. So Rutherford, it's important, discovered the nucleus, discovered it was positive, discovered it was like solid, it was dense, and that most of the volume of the atom is empty. You guys take tremendous notes. Yes, ma'am.
Wait, you said you discovered it was positive.
Like solid, like it was a substance, like it was a dense, hard thing. Because I didn't do a very good job, and it's because really it's not a model that was accurate for very long. But the plum pudding model, that was Thomson. He said that the plums, and let's use, that's gross. How about the chocolate chip cookie model? You with me? The chocolate chips represented the electrons, and everything else around it was like just some positive aura of that balanced out the negative. They had no idea there was actually something in the middle that was the positive that balanced out the negative. All right. I haven't marked roll yet, so let me get on that. Oh, this is like the best attendance we've had in a long time. Welcome back, people who have had issues at home. Glad that you're okay. All right. They call this the nuclear atom because it has a nucleus. Easy enough. All right. Now, here are some things to just make sure you know. J.J. Thomson discovered the electron was negatively charged, and we typically give an electron a -1 charge. Rutherford is credited with discovering the nucleus and really the proton, and it balances out the electron, so it typically is described as a +1 charge. All right, now Rutherford actually was not able to prove that there was a neutron. He hypothesized there was one. The neutron was the hardest of the 3 parts to find, and I want you to tell your partner your guess on why it was the hardest one to discover. Ready, go. All right. So any guesses? No one? Because it's neutral. The tools they were using to study had charges. You could either fire electrons at it or beta particles, which turns out, by the way, are the same thing. Mind blown. Or you could shoot alpha particles. So you had to study it based on charges. But if something's neutral, it doesn't react to charges. So it took a guy, not really Rutherford, what was his name? I think John Newlands was the one that was able to finally prove the neutron. Now, Rutherford was pretty smart about it. The amount of electrons and the amount of protons didn't seem to account for the total mass. So he said, hey, there must be something in there besides just pluses. And also, there was no reason or logic back then as to why the nucleus itself should stay together. The nucleus really should blow apart because everything's the same charge. So you have all these pluses in an extremely close proximity to each other. That should not exist. They should fly away. So they have what's called electrostatic repulsion, which is roughly times 10 to the 9th power. That's pretty strong because gravity is to the negative 27th, like negative 7th. How have I forgotten that number? 6.67. No, negative 11th. I just had to run the whole thing. So gravity, like I fall over and the planet pulls me down with a force roughly times 10 to the negative 11. That's just like a super weak force, and gravity will break my bones. All right, but I can overcome gravity with electrostatic really easy. I can do it right here in front of everybody because I'm magic like that. I can take this magnet and overcome gravity by going like that. Thank you. I'll be here all week. Thank you. Okay. So you guys are awesome. So that force is way stronger than gravity, right? So the nucleus should push apart way stronger. Like when these are oriented the wrong way and they're like weird, like they should just explode. I can force them together, but then like they shoot right off, right? That should happen to a way stronger, but so 20 times stronger than gravity, magnets. And so there was something else. We don't study it a ton, but I'm a physics guy, so I like it. And there's this force called the strong force. And the strong force, and you're like, they made that up. Well, sure, they didn't make it up. It's studyable, but it's the things that keep these together. And it's roughly times 10 to the 20th. So it's basically 10-0 stronger. So it holds them together. You want to hear something else kind of weird about it? These things, I love it. I wish I taught physics. The strong force exists because the strong force exchanges gluons. I'm not making this crap up. All right, between the protons. Now, how does that happen? No one knows how that happens. But that exchange of gluons is what keeps the nucleus together. Nuclear bomb, by the way, is when we distort the shape, because the strong force is super strong, but it only works over extremely small distances. So what we do is we get an atom, we make it have a ton of neutrons and protons, protons. That's why all the nuclear ones are lower on the periodic table. They're giant atoms. These protons don't like each other, but they are sticking together because they are an atom. But we take two of these big fatties, we put a stick of dynamite right here, basically, light it on fire and throw those at that. And then it makes a distorted shape, which is too far for that to work. And then everything explodes 31-0 stronger of energy than gravity, which if I fell over right now, I'm old enough I'd break my hip. Right? Imagine falling over with 31 more zeros behind your force. This is some really big, cool stuff. And that is not on your test, but I find it interesting. Next slide. Okay. Oh, James Chadwick. Who did I say it was? John Newlands, huh? What did he do? He's something. Yep, there's my Wikipedia right there. Hit that up. Okay. I think he helped right? That's all you musicians out there. Just kidding. We'll talk about it. All right, here we go. We got that. James Chadwick, 1932. He finally put together neutrons. You don't have to know Chadwick's name. I mean, he's kind of important, but for some reason, we don't care about him. Okay. So this table, now I really think most of you know it, so you don't have to draw every single part of it. But definitely know proton is positive and it has a mass of roughly 1 AMU. The neutron is neutral and has a mass of roughly 1 AMU. We basically say the proton and the neutron have the same mass. They have a slightly different mass because they're made up of different quarks. Go ahead.
What did they base like the AMU? Why is it not just perfectly one? And why did they put 0073? Like they could just move it and then right.
That's a super good question. The AMU is based on the pure mass of a hydrogen atom. Now, if you look up there, the hydrogen atom is 1.00794. So then you're like, what? And I don't know. I agree. What? But it's essentially saying the proton's one, and that is one. And once again, they're made out of two different styles of quarks. It's really interesting, but not in the class, so I'll skip it. And then we say roughly the electron is around 1/2000th the mass of the proton or the neutron. You do not have to have these memorized. I mean, you should know it's a 1, a 1, and basically a 0. Because if I'm on my scale and I have a quarter in my pocket, I'm not that worried about it. That's not that big a deal. Because my mass is roughly 2,000 quarters. So just taking one off on my scale, is it even going to register? No. So it's not that big a deal. I have no idea, by the way, how many quarters I weigh. I just made that up. Okay. This is like kindergarten chemistry right here. When you look at the periodic table, you must know the following things. The letter is the symbol. Okay with that? Nice. Still good. Elements are symbolized by 1 or 2 letters. The ones that have 1 are typically the ones that were discovered early, and later ones, and that's not perfect, but later ones typically had 2, or if 2 things like carbon and copper, they've been known forever, but they, for us, both start with a C, so they can't both be C and whatever. There are some logical rules to how these weird things show up. So we have the symbol of the element like carbon. Then there's 2 numbers. Do not memorize them as bottom and top because there's no requirement there. It would be nice if the world just said, all right, the mass is always on the bottom and the whatever's on the top, like, but they don't. So memorize the following. The smaller of the 2 values is always the atomic number. Because you'll see C6 and you'll see C6. They're the same thing. It just depends on who typed up the periodic table and how they were feeling that day. All right, all atoms of the same element have the same number of protons. The number of protons defines the element. If we change them, then it's not that element anymore. All right, this won't really matter for a few chapters, but we'll come back to it eventually. The atomic number is known as Z. Typically, Z is also equal to the number of electrons, as long as it's a neutral atom. Okay, the mass number is the bigger of the 2 values. The mass of an atom in atomic mass units is the total number of protons and neutrons in the atom, where we ignore the 0.0073 and 0.0084. We just treat them as ones. Okay. So far, okay? Okay. So once again, be ready to see them in both ways. So like Na could be 12 and 11, or Na could be 11 and 12. The 23. I don't know what I'm doing here. That's the number of neutrons. Sorry, the mass is 23. I'm dying inside. They could be flipped. Don't memorize up or down, memorize the larger or smaller value. All right, isotopes. So this is something definitely tested, definitely a topic AP feels is important. So make sure that you're okay with isotopes. So just a second ago, I said that the protons define the atom, right? So every atom has a definite or an exact number of protons, but every atom does have the chance to have different numbers of neutrons. So iso, this prefix basically means the same. So this word isotopes means same types. It's, I don't know, basic translation from Latin, same types. So an isotope is the same type of atom, but it has different numbers of neutrons. So if you look at this example, all of these are carbon. They are all carbon because there's a C, but really they're all carbon because this is a 6. And if that ever changes, it's not carbon anymore. But this top number is the mass number. So this carbon has a mass of 11. This carbon has a mass of 12. Well, if the protons can't change, then what has changed? The neutrons. So if you look, carbon 11 has 5 neutrons. Carbon 12, the most common one, has 6 neutrons. I'm just scribbling now. This has 7, and this has 8. But they are all considered the same type because all 4 of them have the same number of protons. Go ahead.
Does the number of neutrons like affect the atom at all?
It can determine its nuclear properties and some of its physical properties. Like carbon 12, that's like diamond and graphite and the carbon we're used to. Carbon 14, that's radioactive, and it's what we use to date things that are really old. Like we find a prehistoric bone and we carbon date it. We're seeing what percentage of carbon 14 is left, and then we use half-life, and we'll do that later in the year. But yeah, it does change their properties. Typically, the farther away from being equal to each other, the more unstable. And now that's, when I say typically in this class, this class kind of stinks because math, you do addition and the answers are always the same. In chemistry, it's like some of the time, most of the time, or I don't really know, but at least this one time it did. All right, so there's a lot of issues. So I never hardly say absolutes, but generally the farther away you get, the more radioactive it will be because it becomes unstable. Because you need neutrons to hold it together. Go ahead.
Are you allowed, is it like possible to fire neutrons?
Yeah, 100%. That's basically what we try to do to make a fission bomb. Is we light it up with neutrons, get the whole thing to explode. Typically, it's hard to get just neutrons, but I mean, we can do just about anything right now. One thing they do a ton now is they have particle accelerators, and they'll put a proton or a neutron, whatever. They'll put it in this gigantic loop, like 10 miles, and speed it up to close to the speed of light. And then they have that run into the other one and just see what comes out. And they have these computers. You don't see things, but electric and magnetic fields are created. And then they study and realize, hey, this is made out of something that always spirals, something that like goes all janky or whatever, like, and they study those shapes. It's really fascinating science, in my opinion. I'm not smart enough to understand it, but I enjoy it still. Okay, so an isotope is an atom with the same number of protons but different numbers of neutrons. You do have to know how to pick an isotope out of a list. So what I mean by that, you do have to do this. If I were to say which of the following are isotopes, and I would have like TC, and then I have 43, and then I'd have 96, I'd have TC 43 and 98, and TC 43 and 100. One of these is the isotope and one is not the isotope, or two of them are not. And this is how you know which is the isotope and which one isn't. You look at the list and then you look at the periodic table. Samantha, will you lift your hand straight up? Just point to the sky right now. All right, it's just to the right of where her hand is. TC, you guys see it? Okay, it's one of the white ones in the middle. You look at it and its mass in parentheses is what? 98. So this one would be defined as the non-isotope, and these two would be the ones. Sorry, go ahead. Absolutely. Every test you'll have a periodic table. Same question? Yeah. No, you'll have one every single test. It does not have names though. That's why that part's important. Go ahead.
Who decided that it was 98 and not 96? Because 43 times 2.
That's coming on. We're coming right to that. All right. And they're usually not half and half. There's usually more neutrons, but we'll talk about it. Okay, so one more time, the way to recognize the non-isotope, that's the one listed on the board. It's the representative atom. Everything else is the isotope. Barely got the mic off for that sneeze. All right. Raise your hands if you feel like you could identify an isotope given a list of atoms and their masses. Okay, you do not have to be given this part, and you won't most of the time. You just need their masses. Okay, now listen, pretty much every atom has isotopes, which means like even hydrogen, it's super simple. It's one proton and one electron, but sometimes you'll find a hydrogen that has a neutron. Or two neutrons, and then you're like, what the, right? So deuterium or tritium is what they're called. Now, if you look, what we're going to talk about is how we account for there being three types of hydrogen, or what we'd say two isotopes and one more. So if we ever say how many isotopes there are, add one, and that's the total number of types there are. Well, that's weird, but remember, one's a non-isotope because it's the one on the board. Okay, so what we're going to learn in the next 10-15 minutes is how on the periodic table we account for all three styles when we find its mass. And a good analogy is if you have a red bean, a black bean, and a white bean, and you want to find the mass that represents all of them. We're not going to list all three. If we had beanium, remember this lab from normal chem? To count all the beans. All right, we don't list all three versions. We take their relative average masses and we do it. So that's coming up. But here we go. We have what's called mass spectroscopy when we talk about something's atomic mass. All right. Moving on. Atomic mass is way more complicated than you ever thought it was. In AP chemistry, I'm super good at taking something that you understand and making it so complicated you don't understand it. I get paid to do that. That's how cool my job is. But I think we'll get through this just fine. So atomic mass is not just adding the protons and neutrons, because that's just not good enough for us. So I don't know how many years ago, but a mass spectrometer was invented to measure masses of atoms and isotopes extremely accurate. And AP loves you answering questions from a picture or a graph or a table. So that's why they love these questions. So this is basically how a mass spectrometer works. They take a sample of whatever atom or whatever they're studying. It doesn't have to be an atom, it can be a molecule, whatever. Whatever they're studying, and they make it a gas. And then they ionize it, so it picks up more electrons than it should have. And then, this will be good. I won't hurt myself. Then they fire it through this extremely strong magnet. So you have a charged substance coming through here. All right. And as it goes around the corner, it will deflect at different angles depending on how large it is. Remember the alpha and beta? We had to separate a little bit different because one was bigger, one was smaller. So what they do is they measure these deflections and they count how many there are. So for this example, I just made it up. They fire a gas through here. They get a charge on it. It goes around and it deflects different angles into two separate angles. And so we would say that this substance has two main parts, the isotope and the non-isotope. Now, for this discussion, I'm just going to say they're all isotopes. And I know that will bug you based on what I just said, but we're going to say this substance has two isotopes. The two isotopes are, let me erase. It's on this graph, but we'll just look at it for a second. They are 37 and 35. They have this set up so they know where things with masses will hit. So they can determine 37 and 35. And they'll get a graph. The graph would look like this. I'll just undo all this. So it would show, and I made this up, but it's pretty accurate. It would show that most of the things that interacted with this had a mass of 35, but some of them had a mass of 37. So we would think, all right, what element on the periodic table has a mass a little bit above 35? And you would look, and chlorine has a mass of 35.433. It's closer to 35. Look up here for a second. It's closer to 35 than 37 because there's more of it at 35 than there is 37. Okay, we're gonna pull this together. This is a picture of what we call mass spectroscopy. It's the spectrum of masses from a mass spectrometer. Okay, now this is in your reading. I'm sure you read it last night. Shows you the same exact thing. The gas, it's ionized, it goes around the corner, gives you two. It consists of two isotopes. Okay, here's your sign, one tall, one small. So our mass, we would assume, has to be pretty close to 35.5. This was supposed to be highlighted, whatever. The extent to which the ions are deflected by the magnetic field depends on their relative mass to charge ratios. Okay, now let's look a little bit deeper and ask some questions from the AP test. These are money questions. Like you get these right in 10 seconds and move on. Because if you can answer a question fast, you won. All right, I know this is hard to read, but that's just the way it imported. It says, which of the following elements has the mass spectrum represented above? All right, so it says NB, and that is right above Samantha this time. It's 92.9. Thank you. It has MO, which is right next to it, 95.94. Then it has uranium as an extremely good distractor. That's right by Samantha's head. All right, it's the bottom row, and it has a mass of 238.02891. Now, this is an extremely good distractor. It's super wrong, but what's the atomic number of uranium? 92. So it's like, oh, yeah, it might be that one. And then CR is right above MO, and it's 51.99. What's that? You're right. That is CF. What is that mass? 251. That makes a lot more sense. All right. That's right, was behind Isaac's head. Okay, so looking at this and looking at that table, and I know you barely, like, I don't even know what's going on yet. Will you try and figure it out with your partner? Okay, it is. Okay, so it's definitely not the bottom two, right? They were just trying to trick you with atomic numbers. Thanks for finding the F. So it's one of these two. Now, don't be embarrassed because remember, some of you might not just vote. Who thinks it's 92.9? Who thinks it's 95.94? Okay, well, it is 95.94. And the logic behind it, y'all got it right, so you don't need a ton of help with it, is a lot of the isotopes, like way high up here, are past 92. The mass has to be significantly above 92. This one, you'll notice 95 is about here and here. So about half and half. So it'd be pretty close to the center there, or 95.94. Okay, these questions are not intended to be hard, but they're intended to be like, hey, these are good questions because you got to look at a graph and think. All right, let's look at the next one. All right, it says the mass spectrum, that's this picture, of a sample of a pure element is shown above. Based on the data, the peak at 26 AMU represents an isotope of which of the following elements? Okay, fire away. Oh, can you read this? This says Al with 13 neutrons. This says Mg with 14 neutrons. This says Fe with 26 neutrons and Ti with 26 neutrons. Okay, take a minute and try this one. Sorry, that's probably hard to read. Yeah, it was definitely not there when you took it. It's actually extremely easy because that's in the book. There's two. Yeah. All right, here we go. Anyone think it's A, B, C, and D? All right, the answer is B. The answer is B. And here's why. If you look at magnesium, its mass is 24.3. Are we okay with that? So see how this is much higher than the other two? We would expect then that the mass of whatever we're talking about listed on the periodic table is very close to 24, but a little bit above it. Okay, so aluminum is a mass of basically 27. We would have to have a peak way over here to offset that one. So it can't be that one. And then this one again, they're just trying to mess you up with atomic numbers instead of atomic masses. So here's how we know one more time that it is Mg. Its most likely mass on the periodic table is 24 grams, and then it's 2 over. Now follow this, and I know I'm talking a lot. I do that. Mg has an atomic mass of 24, which means it has 12 protons and 12 neutrons, usually, right? But this isotope has a mass of 26, so it must have 2 more neutrons than we would expect. Okay, so there's a couple layers of thinking in there, and that's why they like these. The last one, it was too hard to clip, so I put it right here. Nope. Oh, that's where the highlighted one is. I put it right here. The mass spectrum of the element antimony. So SB is far right. Isaac, put your hand straight up, and a little bit to the right of that is SB. You with me? I could get my laser pointer. It's just all the way over there. It's such a long walk. All right, there's SB. So if you look at it, it has a 51 and a 121.7. Okay, So the mass spectrum of SB element is most likely represented by which of the following? So this one with one single line at 122. B, a 121 and a 123, where 121 is slightly higher than 123. C, a 120, a 123, and a large one at 124. And then D, 120, 121, and 124. It's hard because they're not all on the same screen. Discuss and see if you can answer that real quick. So there's A, B, C, and D. Okay. Anyone think it's A? Perfect. You may not know the right answer, but at least know the wrongest answer. That can help you in AP. There's never going to be one on the AP test that only has one line. If it was, then you'd look at antimony and be the only one on there with a whole number for its mass. And I know you're like, wait, TC is 98. It's also in parentheses. All of them that are in parentheses are radioactive, so they'd like decay. So their masses are different, but you won't see one. What's that?
They're educated guesses.
They're educated guesses. Okay, who thinks it's B? Raise your hands. Okay, B is the correct answer for the following reasons. These are somewhat close. Dang. I can't even lift my arm anymore. These are somewhat close to each other, right? So the mass is going to be about in the middle. But one's a little higher than the other, and it's this one. So the mass of this, when you average them out, will probably be a little less than 122. Okay, the other ones, the masses are going to be too high, way too much, way too much. Are you kind of okay with this? I have a couple on my test. They're supposed to be like softball, not the hardest things that you're ever going to do in this class. Mass spectroscopy. Okay, I hear some rumblings of chairs, but just let me have this last 2 minutes. The way we get these numbers are from the graphs. We take what's called the average mass, and I'm just going to come right down here. Average mass is calculated from the isotopes of an element weighted by their relative abundance. So we found out that chlorine had two isotopes, 35 and 37. From the graph, we realize that 90% of chlorine is Cl35. So you take 35, the mass of the isotope, and multiply it by the percentage as a decimal. And we come up with 31.5. And then we go 37 is 10% of the sample. So we take 37 times 0.1, and then we add the two of them together. Now, this isn't perfect if you're looking. I made all these numbers up, but it was just for easy math. So we take the mass, and we'll do it again. Don't think, oh, he taught me in 2 minutes and he's going to test me. We'll do a practice one, I promise. We take the mass, multiply it by its percent for all the isotopes, and then add them all together. What do you think? No? Well, we'll do it tomorrow. Anyone else in her boat that has no idea what I just said? Okay, you're not alone. All right, we'll get there tomorrow.
So the circle number is the average.
What we call the relative average mass. Okay, by the way, that's why the masses on the periodic table are not whole numbers. What's that? These will be exact values, so no. All right, I hope that went okay, Zoomers. Brooklyn, hopefully you're feeling well. If you have any questions, hit the chat. If not, go ahead and leave the meeting. I'm gonna stop it.